Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to this lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 6 of module 1, wherein we are discussing the aspects of conductance. In our previous lectures, we have seen the migration of ions and we have also seen the determination of transport numbers using moving boundary method and Hittov's method. We have seen some of the numericals based on it. Also, we have seen the Kohlrausch law. We have started discussing the applications of Kohlrausch law in previous lecture. Now, in this lecture, we will continue to see the other applications of Kohlrausch law. So friends, one of the important application of Kohlrausch law is the determination of degree of dissociation of weak electrolyte. Now, whenever the electrolyte do not ionizes completely, we call it as a weak electrolyte. And the fraction of total number of moles dissociated at any concentration is called as the degree of dissociation at that concentration. It is particularly denoted by this alpha, that is the number of moles dissociated upon total number of moles. Now this alpha can be determined using the Kohlrausch law. How can we determine? So initially we know that the equivalent conductance at any concentration, that is lambda c, is directly proportional to the number of moles dissociated, while the equivalent conductance at infinite dilution is the sum of this lambda c plus lambda a, that is equivalent conductance of cation plus equivalent conductance of anions, and it is proportional to the total number of moles, and therefore my degree of dissociation is nothing but this lambda c upon lambda 0, that is equivalent conductance at infinite dilution. And therefore now this lambda c I can calculate experimentally, and this lambda 0 at infinite dilution, that also I can calculate using Kohlrausch law, and therefore using with the help of Kohlrausch law I can determine the degree of dissociation. This is how simply I can determine the degree of dissociation using the Kohlrausch law. The another important application of Kohlrausch law is the determination of solubility of sparingly soluble salt. We know that certain salts saturate the solution at very low concentration, and such salts are called as sparingly soluble salts. The concentration of solution is so small that it can be considered as infinite dilution. Now since the solution is saturated, this can be taken as solubility of the salt. We denote the solubility of the salt by S, capital S. Now according to the definition of equivalent conductance, what we have, this equivalent conductance is equal to specific conductance upon the concentration. Now this kappa is the specific conductance and C is the concentration equivalents per meter cube. But as the solution is saturated, concentration is equal to solubility, that is C is equal to S, and therefore I can substitute this value over here, and therefore solubility is equal to specific conductance upon infinite dilution, equivalent conductance at infinite dilution. Or I can substitute the other value of this lambda 0, that is specific conductance upon lambda plus lambda minus, that is nothing but in other sense this is nothing but equivalent conductance at infinite dilution. Also this KSP, that is the solubility product, is related to solubility as KSP is equal to S square for univalent electrolyte, that is of AB type, and KSP is equal to 4S cube for unibivalent electrolyte, that is of AB2 type. So I can determine this solubility product as well using this particular formula. Once the solubility is determined, I can determine the solubility product using these formulas. The next important application of Kohlrausch law is determination of ionic product of water. Say this ionic product of water is defined as the product of ionic concentration of H plus and OH minus ions in its pure water. Now it is given by Kw is equal to H plus into OH minus concentration. According to Kohlrausch law, this infinite dilution equivalent conductance at infinite dilution of water is nothing, can be represented as this lambda of H plus lambda of OH minus. Now this is having values of this much, and therefore I can have values of 548.3 Siemens centimeter square per equivalent, Siemens centimeter square. Now equivalent conductance is equal to specific conductance into volume of water in cc containing 1 gram equivalent of ion, and therefore volume of water containing 1 gram equivalent of ion is equal to equivalent conductance upon specific conductance. If I substitute the value, I get this, and therefore 1 centimeter cube of water contains 1 upon 98.97 into 10 to the power 8, which is equal to 1.01 into 10 to the power minus 10 gram equivalent, and therefore the concentration of H plus or OH minus ion is 1.01 into 10 to the power minus 10 gram equivalent per centimeter cube. That is nothing but 1.01 into 10 to the power minus 7 moles per liter. Both the number of both the ions are equal, and therefore Kw is equal to H plus into OH minus, which is equal to this, and therefore ionic product of water is 1.02 into 10 to the power minus 14 is the case. We can have the numerous number of numericals based on whatever we have seen just now as an application of Kohlrausch law. Let us see this numerical. The equivalent conductivity of HCl and sodium acetate at infinite dilution are 380 into 10 to the power minus 4 and 80 into 10 to the power minus 4 Siemens meter square per equivalent respectively. So the transport number of H plus in HCl is 0.84, and that of acetate ions in sodium acetate is 0.56. Calculate equivalent conductance of acetic acid at infinite dilution. It is very simple. The numerical is very simple that way, because we have got equivalent conductance at infinite dilution of HCl, which is equal to this much Siemens meter square per equivalent, and for sodium acetate it is given as this much. So for acetate ion, I can calculate, I can straight away write down, because the transport number is given, and therefore the determination of equivalent conductance using transport number formula we know. So equivalent conductance of acetate ion is equal to equivalent conductance at infinite dilution of sodium acetate into transport number of acetate ion. So if I substitute the values, I get 44.8 into 10 to the power minus 4 Siemens meter square per equivalent. Similarly, for hydrogen ion, I can calculate this quantity as 319.2 into 10 to the power minus 4 Siemens meter square per equivalent. And if I substitute this in this particular splitting of equivalent conductance of acetic acid at infinite dilution is equal to the equivalent conductance of acetate ions plus equivalent conductance of hydrogen ion individually. If I substitute here, I get 364 into 10 to the power minus 4 Siemens meter square per equivalent. So this way I can calculate the equivalent conductance of acetic acid at infinite dilution. Since acetic acid is a weak electrolyte, I have this is one of the method using which I can calculate the equivalent conductance of acetic acid at infinite dilution, and this is particularly the method which we have seen in our previous lecture, wherein we have used the transport number to calculate the equivalent conductance of weak electrolyte using a weak electrolyte at infinite dilution. Similarly, the next numerical is if the equivalent conductance at infinite dilution of sodium acetate, HCl and NaCl are respectively given 91 into 10 to the power minus 4, 426.16 into 10 to the power minus 4, and 125.45 into 10 to the power minus 4 Siemens meter square per equivalent respectively. Calculate equivalent conductance at infinite dilution for acetic acid. Again, this is three electrolyte method which we have seen in our previous lecture. This method we have used. So simply I will write down the splitting of in equivalent conductance of acetic acid at infinite dilution, which is equal to equivalent conductance of sodium acetate plus equivalent conductance of HCl minus equivalent conductance of NaCl. If I substitute their values over here, I can get the value of equivalent conductance of acetic acid at infinite dilution as 391 into 10 to the power minus 4 Siemens meter square per equivalent. This is another application of Kohlrausch law, wherein I can utilize the method of three electrolyte for the determination of equivalent conductance at infinite dilution of weak electrolyte. Similarly, the next numerical is the equivalent conductance at infinite dilution of H plus and CH3CO minus acetate ions are 349.8 into 10 to the power minus 4 and 40.9 into 10 to the power minus 4 Siemens meter square per equivalent respectively. The equivalent conductance of 0.01 normal CH3COOH acetic acid was found to be 16.3 into 10 to the power minus 4 Siemens meter square per equivalent. Find the degree of dissociation and percentage dissociation of acetic acid at this concentration. The numerical that way is very simple. I can find out the lambda C at that particular concentration, 16.3 into 10 to the power minus 4 Siemens meter square per equivalent, which is given over here. Then equivalent conductance at infinite dilution has this formula. So if I substitute the cationic equivalent conductance and anionic equivalent conductance respectively, so I get the overall value of equivalent conductance at infinite dilution is equal to 390.7 into 10 to the power minus 4 Siemens meter square per equivalent. Now my definition of alpha is lambda c upon lambda 0. So if I substitute the respective values over here, I get 0.041 as degree of dissociation. Now percentage dissociation is simply I can calculate it as the percentage of this is nothing but 4.1%. So 4.1% acetic acid has been dissociated at this particular concentration. The next numerical is from the following molar conductance at infinite dilution, calculate molar conductance at infinite dilution of NH4OH. I have got these values of barium chloride. Molar conductance of barium chloride is this much. Molar conductance of barium hydroxide is this much. Molar conductance of ammonium chloride is this much. This is given. So I have these values of molar conductance of barium chloride, barium hydroxide, and ammonium chloride. I can split up these equivalent conductances into their cation and anions. If I respectively write down barium chloride as Ba2 plus and Cl twice Cl minus, barium hydroxide like this, and ammonium chloride like this. So I can represent these molar conductances in this form of A, B, C. Now, if I follow this particular algebra, B plus into 2 into C minus A. So if I substitute this, what I get, if I substitute this value according to this, if I follow at what I get 2 into ammonium ion equivalent conductance plus 2 into hydroxide ion equivalent conductance. So that gives me ammonium hydroxide 2 times molar conductance of ammonium hydroxide, that is nothing but 4.766 into 10 to the power minus 2 Siemens meter square per equivalent, and therefore the molar conductance of ammonium hydroxide is nothing but 2.383 into 10 to the power minus 2 Siemens meter square per equivalent. This is how I can utilize the Kohlraasch law in number of ways, and I can solve n number of numericals based on the logic of Kohlraasch law and the various applications of Kohlraasch law. Now next, one of the very important application of the Kohlraasch law is the application in terms of the conductance measurement, that is to determine the hydrolysis constant. So this Kohlraasch law can be utilized in determining the hydrolysis constant. Now what is hydrolysis? When a salt of weak acid or weak base is dissolved in water, it reacts with water molecule to give excess of hydrogen or hydroxide ion, and this process is called as hydrolysis. The extent of hydrolysis basically varies with the type of electrolyte and the extent to which it is diluted. So it is measured in terms of basically hydrolysis constant. So one can determine the hydrolysis constant of weak acid or weak base using the Predict's method. For this, let us consider an example of hydrolysis of aniline hydrochloride here. Okay, now it is the salt of weak base aniline and strong acid HCl, that is hydrochloride. When it is dissolved in water, it undergoes hydrolysis as this particularly. Okay, so at initial concentration, if you see the complete dissociation is 1, and both the aniline ion and hydrochloride is 0, 0. Now when it dissolved in water, it hydrolyzes to some extent, and when it hydrolyzes some extent at equilibrium, the degree of hydrolysis H, in terms of degree of hydrolysis H, it can be represented as in case of aniline it is 1 minus H, and for aniline it is H, and for HCl it is H. Okay, so the total conductance of solution is due to HCl and unhydrolyzed aniline hydrochloride, because aniline being weak base is poorly ionized. Okay, and therefore my equivalent conductance will be, the equation of equivalent conductance will be 1 minus H into lambda C of aniline hydrochloride and H into equivalent conductance of HCl, isn't it? No, as we said that this aniline cannot be or it is, since it is purely ionized, it will not take part into hydrolysis part, and therefore this H I can calculate using this expression as H is equal to lambda minus lambda C upon lambda HCl minus lambda C. And once this H can be calculated using these values, where this lambda C and lambda HCl, they are the equivalent conductances of the unhydrolyzed salt and the free acid, which can be determined using Kohlraasch law. And since this can be determined using Kohlraasch law, I can determine the hydrolysis constant using the Kohlraasch law. And once my hydrolysis constant is known, I can determine the hydrolysis constant, that is Kh, in this term, that is H square C upon 1 minus H, where H is hydrolysis constant and degree of H is the degree of hydrolysis and C is the concentration. Okay, so H is the degree of hydrolysis, which we can substitute in this particular expression, and I can calculate basically the hydrolysis constant Kh using this formula. The another important application of conductance measurement is the conductometric titration. Now there can be various and many n number of types of titration which I can calculate. So there are several types of titration. We will see one by one all the titrations based on it. This titrimetric analysis is used for long time to determine the concentration of various solutions. Now, and the aim of the titration is to locate the equivalence point of the analyte and titrant. So titration in which the equivalence point is located on the basis of conductance measurement are called as basically conductometric titrations. In these types of titrations, the titrant is taken at least 5 times more concentrated as compared to the analyte. This is basically the reason behind this is to avoid the volume increase during the titration. And the different types of conductometric titrations will be discussed in few of the slides hereafter. Okay. So first slide, we will see the first titration, that is titration of strong acid with the strong base. So let us consider a titration of strong acid HCl with the strong base NaOH. So initially the solution contains only hydrochloride, that is HCl, which dissolves as HCl as H plus plus Cl minus. Okay. So HCl plus plus Cl minus will give me whenever it goes in solution, it is going to remain in this particular form. When NaOH is added from burette, it reacts with HCl in this form. Okay. So this is a basic acid base titration. So acid base reaction is this particularly. So my net effect is the replacement of H plus and Na plus ions. Since conductance of Na plus is less than H plus, the conductance of solution goes on decreasing up to the end point. After the end point, NaOH remains unreacted in the solution and dissociate as NaOH as Na plus plus OH minus. So OH minus has higher mobility and so conductance goes on increasing after the end point. So the conductance is recorded and plotted as a function of volume of NaOH. The graph is shown here and the intersection of two lines gives the end point, isn't it? So you can see initially the effect wherein H plus ions are utilizing on the addition of NaOH. So H plus and OH minus, they are combining and therefore the conductance is decreasing. At this point when it comes, so now after this point Na plus and OH minus ions they are remaining in the solution, and because of the conductivity of hydroxide ion, the another sharp increase is observed. So these two sharp lines are observed. When we take the intercept of these two lines, we can observe the equivalence point of this particular titration. So in case of strong acid and strong base, using the conductometric titration or conductance measurement, I can find out the equivalence point of the titration. Now, secondly, the next type of titration is the titration of strong acid with weak base now. So acid is strong, but the titration with which we are doing is weak base. So now consider the strong acid of HCl and weak base of ammonium hydroxide. Initially, the solution contains only hydrochloride HCl, which dissociated as HCl giving H plus plus Cl minus. So the conductance is because of this H plus ions. Now when NH4OH is added, ammonium hydroxide is added, it reacts with HCl as this H plus plus Cl minus plus NH4OH. It will give NH4 plus plus Cl minus plus H2O. So H plus is combining again with the hydroxide ion. So the net effect is the replacement of H plus with the ammonium ion. Now, since the ammonium ion has got less conductance than H plus ion, the conductance of solution goes on decreasing up to the end point. And after end point, what happens? After end point, the ammonium hydroxide does not dissociate because it is a weak electrolyte and conductance remains constant. So the intersection of two lines gives the end point. So you can see in this figure, initially the ammonia H plus ions are replaced by ammonium ions. It comes to this point, and after end point, basically, since there is no further increase or since the conductance of ammonium ion is not up to greater extent, it remains. This ammonium hydroxide does not dissociate to greater extent, and therefore, since it does not dissociate to greater extent, it remains as a weak electrolyte, and therefore conductance does not increases, and therefore it remains as a straight line. And therefore the intersection of this dropping line and this straight line is going to give you the equivalence point of a strong acid and weak based kind of titration. Okay. The next type of titration is that of titration of weak acid and strong base. So herein acid is weak and base is strong. So consider the titration of weak acid, that is acetic acid, with the strong base NaOH. So initially the solution contains acetic acid which is poorly ionized, and hence the conductance is very small. And when NaOH is added step by step, it reacts with acetic acid as this reaction CH3COOH plus NaOH will give you CH3COO minus plus Na plus H2O. And therefore the conductance of the solution increases slowly due to the formation of ions, formation of these ions. So after the end point, since the end point occur, NaOH dissociated as NaOH giving Na plus OH minus, and due to the formation of additional hydroxide ions with high mobility, the conductance increases very rapidly, and intersection of two lines gives the end point. You can see over here, initially the acetic acid does not ionizes, and as the NaOH is added slowly, because of the Na plus and OH minus it goes into formation of water. So Na plus, the slow increase is given shown over here, and once the endpoint reaches, after that the hydroxide, due to hydroxide ions, this sharp increase in conductance is observed, and therefore the intersection at these two line intersect at the point, and this point gives you the equivalence point of the titration of weak acid with the strong base. The next important type of titration is the titration of weak acid with weak base. So in this particular titration, let us say consider the titration of weak acid, acetic acid, with the weak base, that is ammonium hydroxide. So initially the solution contains acetic acid which is very poorly ionized, and hence the conductance is very small. So when ammonium hydroxide is added, it reacts with acetic acid as this reaction CH3COOH plus NH4OH. So acetate ions plus ammonium ions plus water. So due to the formation of ions initially, the conductance of solution increases very slowly up to the end point. After the end point, again NH4OH remains unreacted and unionized, and since it is a weak electrolyte, so it ionizes very poorly, and hence the conductance remains constant of more or less after the end point, and therefore after the intersection of two lines gives the end point as shown in this particular figure. So initially if you see here, the acetic acid, when you add ammonium hydroxide, so initially the formation of ions, this slow, very slow increase in conductance is shown over here. Once the end point reaches, after that only ammonium hydroxide remains over here, and since it is a weak electrolyte, it does not ionizes, and therefore the conductance does not increase, and therefore it remains this steady in this particular reaction. So this is how we can find out the equivalence point in case of weak acid with weak base. Apart from that, the next type of titration is titration of mixture of strong and weak acid with the strong base. This is the interesting case. So if we mix the strong acid and weak acid, and we titrate with the strong base, how can it give you the pattern or two different endpoints that can be observed over here? Say consider the mixture of hydrochloric acid and acetic acid to be titrated with NaOH, isn't it? So here HCl is a strong acid while acetic acid is a weak acid. So initially only HCl is dissociated in solution because the dissociation of acetic acid is suppressed by common ion effect. So when NaOH is added, the following reaction takes place. That is H plus Cl minus will give you NaOH, and this Na plus Cl minus and water, that is water formation. So initially the net effect is the replacement of H plus ions with the Na plus ions, and therefore conductance goes on decreasing very sharply. So you can see over here the conductance decreases very sharply over here. After complete neutralization of HCl, NaOH reacts with acetic acid. So once the HCl is reacted, the NaOH reacts with acetic acid in this form, that is CH3COOH plus NaOH will give you CH3COO minus plus Na plus and H2O. So now in this case, due to formation of ions, the conductance of solution increases slowly. You can see along this line. So after the end point of this acetic acid, the NaOH remains unreacted and dissociate as NaOH giving Na plus plus OH minus, and then due to formation of hydroxide ions with the high mobility, the conductance increases very rapidly. The endpoint are obtained as shown in this particular figure. So initially HCl is consumed first, and then acetic acid neutralization starts. So the intersection of these two lines will give you first endpoint. Then acetic acid is consumed and NaOH remains in the dissociated form, and therefore this intersection will give you the second endpoint over here. So the endpoints obtained in this particular figure is V1 and V2. They corresponds to first endpoint corresponds to HCl, and the V2 minus V1 corresponds to the acetic acid concentration. So this corresponds to HCl endpoint, and the V1 minus V2 V2 minus V1 corresponds to acetic acid endpoint. So this way we can see the conductometric titration for the mixture of strong acid and weak acid with the strong base, and this is how we can utilize this technique of conductometric titration for the titration of mixture of the acids. Next type of titration is conductometric titration for precipitation reaction. Now consider the precipitation reaction of KCl and silver nitrate, potassium chloride and silver nitrate. So reaction can be represented as KCl plus AgNO3 will give you KNO3 plus precipitate of AgCl, silver chloride. Okay. So initially in this solution, solution contains KCl, which dissociates completely. Now when silver nitrate is added, following reaction takes place, that is K plus plus Cl minus, in which the silver nitrate is added. So this silver nitrate, when it reacts with this, the K plus remains into solution, NO3 minus remains, and this silver ion forms combines with chloride ions to give you silver chloride. So the net effect here is the replacement of chloride ions by the nitrate ions. Both of them have almost equal ionic mobility, and therefore the conductance remains constant up to the end point. You can see over here in this particular figure. So since chloride ions are being replaced by the nitrate ions, your conductance does not seem to be affecting due to the titration, and therefore it remains constant till the end point. Now once all the KCl is consumed, this after endpoint AgNO3 remains unreacted, and therefore this AgNO3 remains in the solution in the form of Ag plus plus NO3 minus, and therefore the conductance increases after the endpoint of the particular reaction, the precipitation reaction. So this intersection of KCl and silver nitrate titration gives you the endpoint of this precipitation reaction. Here all the KCl gets consumed, and after this, actually because of the dissociation of silver nitrate, this increase in conductance is observed in this particular reaction. The last part of this particular discussion of conductance is the advantages of conductometric titration over the other traditional methods. So advantages, what are the advantages? So these conductometric titrations are particularly useful in the titration of colored solution for which visual endpoint detection is not possible. Okay, so wherein there are no suitable indicators are found out, or wherein some has a problem of identifying the color. In all such cases, conductometric titrations are particularly useful. Okay, then dilute solutions as well as very weak acids can also be titrated conductometrically. Like weak acids like acetic acid also can be titrated using conductometric titration. No special precautions have to be taken as the endpoint is recorded by the graphical method. we do not have to take any special precaution, because after all results have to be plotted, and it gives you a trend, and the trend after intersection will give you the endpoint, and therefore no special precaution has to be taken here. Visual indicators show color change in wide pH range, hence endpoint cannot be detected. So this is the advantages of conductivity titration over the visual indicator titration, wherein the pH range usually play a vital role in identifying the endpoints or indicator endpoint. And in this particular case, no indicator is used, and therefore it is particularly useful titrations in such cases wherein the process is pH dependent. Now, visual titrations can be carried out between weak acid and weak base, but these titrations can be easily performed conductometrically. So, visual titrations cannot be carried out for such cases of weak acid and weak bases like acetic acid and ammonium hydroxide, but then in conductometric titration, it can be carried out very easily. Now, mixtures of acid can also be titrated simultaneously using the conductometric titration. This is the biggest advantage that we have seen in this particular case. So friends, all in all, the conductometry titration has got lot many advantages over the traditional methods of titrations. So friends, here we have come to an end of this lecture, and with this particularly, we have come to an end of the entire discussion of module 1 of conductance. We have discussed in detail all the aspects of conductance in this particular lecture series, and we have seen almost all the aspects of the measurement of conductance, determination of transport number, the applications of Kohlrausch law, and the conductometric titrations. We will see the remaining part of this lecture series in the next module 2. Thank you.